Hello friends, today we will discuss a very important lemma in the theory of expectations, that is the lemma 2, which says that if I have a non-negative random variable, then I can construct, or there exists a sequence, it is all the same. I can construct a sequence of non-negative valued, monotonically non-decreasing simple random variables which converge to x pointwise, and we'll see what role it plays. So here is the proof. So I have a non-negative random variable on a probability space x. Now I am going to construct the sequence of random variables xn as follows. This proof is constructional, and I'll define this random variable xn pointwise. So take each point or outcome in the sample space. Then I would define xnw as follows. So I know that x is a non-negative value random variable on this probability space. So what does this mean? That means this is a non-negative valued function with domain S. So for every point in the domain S, every w, xw is a non-negative number. So given a natural number, xw is a natural number n, xw is either greater than equal to n or less than n. In case this number xw is greater than equal to n, we define xnw to be n. And in case this number xw is less than n, that is between 0 to n, it cannot be less than 0 because you have taken x to be non-negative valued. Then what we do, we partition the interval 0 to n into n into 2 to the power n subintervals, each of length 1 by 2 to the power n, and then check in which subinterval xw is contained. So in whichever subinterval xw is contained, we take the here there is a typo, so this should be the right endpoint. So I'm correcting the typo. Insert equation by, so I'm taking the rightmost endpoint. I'm taking the rightmost endpoint of this interval. So this value to be the value of the x and w. So now you see what is what we have created. For any natural number n, xn thus created will take what values. It can be either n or it could be any one of these numbers. That is, if xw is in the first interval, that is between 0 to 1 by 2 to the power n, then x and w will be 0. So x and w will take the value 0, 1 by 2 to the power n, 2 by 2 to the power n, up to n n by 2 to the power n minus 1 by n by 2 to the power n, or n. So there are 2 to the power n values that this it's random, that is finitely many values that each xn is taking. So they are simple random variable on the same space. And now you can see that these are non-negative values because all the values of xn's are non-negative. And secondly, why this is so? Because this is by construction. So for each w in S, if xw is greater than n, then xnw is n. So xw is greater than xnw. Otherwise also you see when xw is in a particular interval, I am taking the right endpoint. So by construction, x and xw is always greater than this, greater than equal to the right endpoint. Sorry, the left endpoint. So this will be the xw greater than equal to xnw. I have been saying right endpoint. Sorry, that we are taking the left endpoint. So it's by construction this is true. And these parts require some convincing. Maybe we can talk about it later if it is not clear to you. What you see, to see the relation between xnw and xn plus 1w, what really is the, how do you really get xn plus 1w from xw? You have to partition this interval, you have to into two parts, each of two equal parts, that is you divide it by you make it this will be split into two subintervals, each of length 1 by 2 to the power n plus 1. So that is the real key, and so we can talk about it later if needed. And this part may be a bit unintuitive for you. That what I am saying, that for every w in S, every point in the sample space, there exists a natural number n such that the difference between x and w and xw is less than 1 by 2 to the power n for all n exceeding nw. Why that is so? Because you see, your xw is a fixed non-negative number. So as you are increasing the value of n, 1, 2, 3, 4 and so on, eventually you will get an n such that xw is less than n, right? That comes from Archimedean properties of real number. So that number is the nw. So once you take n greater than nw, so this so those n's are the case where n is your greater than xw, that is xw is less than n. So this part is no longer there. We are looking at this part. So when xw is less than n, then what we check, that for where we divide the interval 0 to n into subintervals and check which subinterval contains xw, and take the left endpoint to be the x and w. So that is the algorithm. So by that algorithm, when n is greater than nw, that is n is greater than xw, so x and w is really the left endpoint of the interval containing xw. So the difference between these two is really cannot be more than the length of this interval. Now what is the length of this interval? 1 by 2 to the power n. So the logic is quite elegant. So you have to look really at x and w as the left endpoint of the interval containing xw. So the difference between these two cannot be more than the length of the interval. So that is why it is less than 1 by 2 to the power n. So what you are getting? So this means as n tends to infinity, x and w goes to xw. So what I have constructed is a sequence of non-negative valued simple random variables which pointwise increase to x. Why increase? We are saying increase because of this relation. So now we can apply, so this is the lemma 2 that we have stated here and proved. Lemma 2 has been stated, this is the proof. So for any non-negative random variable, we can construct a sequence of simple random variables which are pointwise increasing to x. So now apply MCT, because this is the classic case. You have a non-negative sequence of non-decreasing random variables which are pointwise converging to x. So by MCT, expectation of x is equal to limit of xn's. Now what this I have said that when xn's are non-decreasing, so expectations of xn's are non-decreasing. Now a non-decreasing sequence will always have a limit. Now that limit may or may not be finite. So if this sequence is divergent, then expectation of x is not finite. So for any non-negative random variable, you have two cases. Either it has a finite mean, that is expectation of x is finite, or it is and the expectation of x is not finite. But in any case, you can always think of this expectation of x as the limit of expectation of xn's, where xn's are a sequence of non-negative simple random variables that you construct using x. So this is the second definition really of expectation. And now this approach can be used to prove some results which are otherwise difficult to prove. That is, if you take any two random variables on the same space, non-negative valued, then you can easily see x plus y will also be a non-negative random variable. Now what we can prove is that expectation of x plus y is expectation of x plus expectation of y, and this quantity, the expectation of a will be finite provided both of them are finite. If one of them is infinite, this will be infinite. Now this requires a proof. Now if you recall the first definition of non-negative simple random variables that I have defined using supremum, using that approach, this result is we cannot prove this result. But now using this second definition, it becomes far easier, because I'll just give you the hints that x and y are both non-negative valued random variables. So apply this lemma 2. So apply this lemma 2 for x as well as y. So by that lemma 2 which we have proved here, you will get a sequence xn for x and yn for y which are non-negative simple and pointwise increasing to x and y respectively. Now if you add xn plus yn, they will be still non-negative simple. Why? Because sum of two simple random variables is simple, and if xn is increasing and yn is increasing, then xn plus yn is also increasing, and xn is increasing to x, yn is increasing to y, then xn plus yn will also be pointwise increasing to x plus y. This follows very simply if you know a little bit about pointwise convergence and the algebra of limits. So essentially what you will get very easily is that for the random variable x plus y, that we get a sequence xn plus yn which is non-negative, simple, and pointwise increasing to x plus y. So by this definition, by what you get using the MCT, so expectation of x plus y will be the limit of n tending infinity expectation of xn plus yn. And now you have to go back to the property. Remember, xn and yn are simple random variables. That is the key issue here. And now going back to the properties of simple random variable, xn plus expectation of xn plus yn will be additive, and then you have to apply the algebra of limits. So, and that's it. So I'll stop here. So this is a very important topic. I hope that it is understandable to you. I suggest that you listen to this and think about this in a few times.